Welcome to the class on the course ARM Microcontroller and Embedded System. Lecture 1 of Module 1. Module 1 deals with ARM 32-bit microcontrollers. In this video, we are going to see the evolution of the ARM processors introduced into the embedded market by the ARM company and understand the architectural versions of these ARM processors and see the enhancement of the instruction set with respect to the architectural development. ARM stands for Advanced RISC Mission. As the name itself says, all the ARM processors follow the RISC architecture. RISC stands for Reduced Instruction Set Computer. All RISC missions instruction set is said to be simple, which means the mission code for almost all the instructions are of the same size, which allows deeper pipelining to be possible, and that in turn increases the speed of the processor. So all the ARM processors designed by the Advanced RISC Mission Limited follow the RISC architecture. Advanced RISC Mission Limited is a joint venture of Apple Computers, Acorn Computer Group, and VLSI Technology. The point to be noted here is the ARM company is involved only in the design process. They are not into manufacturing and sales. They only design the processor and sell or license that the design to its partners. This type of a business model is what we call it as the intellectual property licensing. The number of partners to the ARM company has increased enormously over the years, and the ARM company also makes sure that it provides enough support to its partners by giving a strong base of development tools, hardware, and software products. Now let us see the architectural versions. The initial designs of the processors given by the ARM company were not able to see success in the market. So the processors ARM 1 to ARM 6 were a failure. In the year 2000 came the processor ARM 7, which was a big hit for 32-bit processors in the embedded market. This was followed by the processor ARM 9 in the year 2003. After which there was no looking back. Then came the ARM 11 processor, and now we have the Cortex family of processors. So we can see that the processors has evolved over the years, and the architectural design, the design of the processors has also been enhanced, keeping few features in mind. The features which were kept in mind for the enhancement were power consumption. So they wanted to give a processor which would work at, which would consume very low power and has power saving modes. And they wanted a processor with high code density to compress more code into a small memory chip. Speed is another main concern. And they wanted the processors to handle even multimedia data for DSP applications. And they even wanted the processors to handle complex user interfaces. So keeping all these features in mind, the design of the ARM processors were improved, which led to the introduction of these processors by the ARM company. So we can see that there was a continuous improvement, and that in turn led to the different versions of the architectures. So ARM 7, which was the first successful processor, falls under the architectural version 4. So we would start here now from the architectural version 4 of ARM. After V4, we have V5 followed by V6 and V7. ARM 7 comes under V4, ARM 9 under V5, ARM 11 under V6, and the Cortex family under V7. But in Cortex family, it is divided into 3 categories or 3 profiles: V7A, A for application; V7R, R for real time; V7M, M for microcontroller. Right? So these are the different processors, and these are the architectural versions to which they belong to. So ARM 7 is the processor number, and ARM 7 falls under the version 4. Right? So students usually get confused between the processor number and the architectural versions. Hope this is clear now. Next, we would study the key feature or the important feature of each architectural version. So in ARM version 4, they started enhancing the design by adding few additional features, And each time a new feature was added, they added a suffix to that particular processor. In the sense, ARM7, we can add the suffixes TDMI, where T stands for thumb instruction support. So the thumb state was introduced in the version 4, which was the highlight of the architectural version 4, which we even write it as V4T. T stands for thumb. Okay, thumb instructions are 16-bit instructions which were introduced in the architectural version 4. D stands for JTAG debugger, which means this is the type of debug support provided. M is fast multiplier, and I stands for ICE module, that is in circuit emulator, which is again a debugging tool for which helps for debugging, right? So these are the suffixes, and each suffix would indicate a key feature of that particular processor design, right? So these features became a mandatory part for the higher versions of processors. So in version 5, we have all the features of that of version 4. So in version 5, they started concentrating more on the memory support. And instead of giving suffixes, they went for number system to indicate the key feature, right? So we have ARM926-946. So here you can see that this 46 and 26 indicate a certain characteristic of that particular ARM processors with respect to the memory. So 26 indicates that it has a memory management unit, and 46 indicates that it has a memory protection unit. And in version 5, they started even enhancing their instruction set by incorporating DSP instructions. So in version 5, they concentrated mainly on the memory support as well as the DSP instructions being added. So in version 6, again, you have the same numbering system for the memory support provided. And then they actually worked on the different types of architectural models that they can have. In version 7, we have the Cortex family. Here they have clearly divided them into 3 profiles. A profile application, A stands for application. An example for that is Cortex A8. And for R, we have Cortex R4. And for M, we have Cortex M3. Actually, the Cortex family comes even under version 6. We have Cortex M0 and M1 under the architectural version 6, right? So these are the different ARM processors, and these are the architectural versions under which each one of the processors would fall under. Now let us see the Cortex family of microcontrollers. As I already told you, we have 3 profiles: A profile, R profile, and M profile. A profile is basically used for complex applications like high-end embedded operating system. So for OS-based processors, we go for the A profile category of processors. R profile is used for real-time systems where reliability is a main concern. Reliability is a major factor which needs to be taken into account. For time critical systems, we would be using the R profile family of R profile category of processors. Next, you have M profile, which is used for microcontroller based applications, which are basically used to provide low cost solutions. So where cost is a key factor, they go for the M profile category of Cortex family of processors. So these are the 3 profiles for the Cortex family of microcontrollers. Now we would look into the instruction set architecture. So the ARM processors support broadly 2 states: ARM state and thumb state. ARM processors are 32-bit processors, which means they're able to process 32 bits of data. So if they are dealing with 32-bit instructions, then we say that we are in ARM state. If they are capable of handling 32 bits, they should be capable of even handling 16-bit as well as 8-bit. So if they are dealing with 16-bit instructions, we say that it is under thumb state. For 8-bit instructions, we would be using Jazelle state, okay, which is not shown here. Right? So broadly, we have 2 states: ARM state and thumb state. ARM state for 32-bit instructions and thumb state for 16-bit instructions. When I say thumb 2. We have now the thumb 2 technology, which is a combination of both ARM state as well as thumb state. So thumb 2 technology combines both ARM state and thumb state together. So if you look at this diagram, you would understand. So you can see that the thumb instructions are a subset of the 32-bit instructions, the ARM state instructions. Okay, and thumb 2 technology is a superset of 32-bit and 16-bit instructions. In ARM 7, we have the thumb instructions introduced, right? So in version 4, we have seen V4T, right? So we have the thumb instructions introduced, but we had to write a separate source file for ARM and thumb instructions, which led to time delay because of the switching between the states, and in turn, this also gave memory alignment problems. So these were the problems faced with the ARM 7 processors even after the introduction of the thumb state. So all the above problems were solved by using the thumb 2 technology, which is a combination of both 32-bit and 16-bit thumb state instructions. And our current Cortex family of controllers support the thumb 2 technology. Thumb 2 technology is supported, which provides significant benefits like the ease of use, code size, and the performance is much better. Would be much better. Now let us see how the instruction set. Now we'll relate the instruction set enhancement with the architectural versions that we just studied. Okay, so the different architectural versions which we just went through was V4, V4T, V5, V5E, V6, and V7. This was the architectural development over the years for the various processors introduced in the market. Now we would relate this with the instructions, okay, the thumb state, ARM state, and so on, the instruction set. So in V4, we had only the ARM state, which means it was supporting only 32-bit instructions. With V4T, the thumb state was introduced, which means we had both 32-bit as well as 16-bit instructions. In V5, they had both ARM and thumb. Along with it, they tried to enhance their instructions by adding instruction set by adding DSP instructions. So when I say E, it means enhanced DSP instructions being added. In version 6, again you had ARM and thumb, along with this, they started in changing the architectural modeling, like they started using SIMD, single input multiple data, and they even provided better memory support. And in version 7 came the thumb 2 technology, wherein the code density could be increased. The code density could be good, and the ease of use also was better. So this, with respect to the architectural development, this indicates the instruction set enhancement. Thank you.